Hello everyone, today we're going to go over 2.3 through 2.4. On Friday you learned about 2.1 through 2.2. Today we're learning about the theory of island biogeography. I always say it wrong. And then we're learning about ecological tolerance in 2.4. So let's start off with 2.3, going over the objectives and essential knowledges. So our objectives are to be able to describe our objective is to be able to describe the concept. So describe island biogeography. And we have a second learning objective, which is to describe the role of island biogeography in evolution. So how does it affect evolution? So those are the two things you should be thinking about when you go over this. So starting off, the study of ecological relationships and community structure on islands. So islands can be actual islands because of bodies of water, or they could be habitat islands, like if we think of Central Park in New York. Here's a picture of it. It's very cut off from any other habitat that animals would be successful in. So it's very surrounded by human developed land. So that would be considered an island as well. So it's not just the typical islands that we think of that are structured in bodies of water. It's also islands of just habitat in general. So there's two basic rules or observations of island biogeography. Larger islands support more total species, and islands closer to the mainland support more species. So going back to the first one, the larger islands support more total species. The larger the island, the greater the ecosystem diversity. So if we have a really, really big island, like Australia is considered an island. I mean, it's its own continent, but it's an island because it's surrounded by a bunch of water. It's not connected to anything else. It has a large ecosystem diversity. If we look at other islands that are, more typical islands, not super large islands, the larger they are, the more diversity they're going to have, because there's more food and there's more habitat resources for those, and therefore there's more niches or more roles for those organisms to play. Islands closer to the mainland can also support more species because it's easier for those organisms to colonize those islands and get from the mainland to that island. Oopsies, I can't read that. And obviously, the more organisms there are, the more genetic diversity there is within the habitat. So here's kind of a graph showing the relationship between island size and distance from the mainland. If you look at this one right here, the island area, as the island area goes up, so does the number of supported species. And over here, as the distance from the mainland increases, so as we go over on the x-axis, as the distance from the mainland increases, the number of supported species goes down. So it's kind of an inverse relationship between island size and island distance. And over here, this is a very bad graph in this reference. I mostly put this on here for this. So larger islands support more species, as we talked about. Larger islands have higher ecosystem diversity because they have more niches. There's more roles because there's different food sources, more places for them to hang out in and live in. If we look at the Galapagos Islands, it's a great example of diversity of birds. Also on larger islands, there's a larger population size, and therefore they're more genetically diverse. The larger the island, the more of one species it can support, and therefore the more genetic diversity there is. There's also a lower extinction rate because there's more food, there's more space than smaller islands. There's a positive correlation between island size. Can I move this? Yes, I can. There's a positive correlation between island size and species richness. So going back to 2.1, when we learned about species richness, there's more species available. What you're supposed to be getting out of this is larger island better for species diversity, closer to the mainland better for species diversity. And as you get smaller or as you get further from the mainland, it's not as good for the species diversity. So if we look at some of the different islands that we know about and looking at the reptilian and amphibian species on the West Indies islands, as the island size increases, they all have a pretty consistent line of increase in the number of species that it supports. So this is just a real world scenario of species diversity and the size of the island in kilometers. So Cuba is obviously the largest one, and so it has close to the most amount of species. We're also talking about the distance to the mainland. So the closer to the mainland, the higher the species richness. There's more species there. It's easier, obviously, for more species to get to and from that mainland or that island if it's closer to the mainland, whether that means they're swimming or whether that means they're flying. More continual migration of individuals to the habitat. So just because they get to the island doesn't mean they don't move back. And so if we are closer to the mainland, let's say we're talking about the finches from Galapagos Islands. If those are really close to the mainland and we have species go off and create a new species on the island, it's more likely that they're going to provide more species diversity to the mainland as well, because they're more likely to migrate back. And that brings more genetic diversity everywhere. Here's a nice little example of this. I think these islands are about the same in size. Maybe not. This one looks a little bit bigger. But it's showing pretty constant migration between this one, pretty constant migration between island A and island B, and pretty constant migration between island B and island C. What doesn't happen so often is migration between mainland and island B because it's further away, or between mainland and island C because it's further away. And we can see that's affecting the species richness, because on island A we have very similar species richness to the mainland. One, because it's large, and two, because it's close. It's the distance from it is close. And then we start going down in species richness. We don't have any blue triangle species over here. And then we only have the pentagon species over here. So decrease in community richness as it gets further away and as it gets smaller. I think we get the idea of this. So the evolution of islands. Islands have limited space and resources, creating unique conditions for evolution. So if a species goes to an island and it doesn't migrate back, it might have different food available to it, and so it might need to adapt to that. So it provides a specific pressure on the species to adapt to those very narrow species, or very narrow niches. They have different zones, and their zones are they're a lot closer together. Adaptive radiation is a single species rapidly evolving into several new species to use different resources and reduce competition. I just read on, I can't remember what the source was, but I just read that a new Galapagos finch species has been created on the Galapagos Islands in just 2 generations, which is insane. And that's because of the different changes in their songs, due to being able to be heard or whatever it was. But adaptive radiation is when they rapidly evolve because of that resource competition or using of different resources. For example, like back in the day with Darwin, their beaks had to evolve very quickly because they needed to do resource partitioning for the resources that were there. At the time, they all ate the same thing, and they needed to expand what they were eating to partition the resources of that island. And so they therefore evolved for those niches. So here's your FRQ for 2.3. If you do turn in a 2.3, or it's on Google Classroom, and if you do turn it in, please email me so that I can give you feedback. Otherwise, I'm not really checking it because not a lot of you are turning it in, but it is highly recommended that you practice these FRQs. I don't think your FRQ is going to get better if you don't practice it. So at least, at the very minimum, take a moment to pause this video and read through this and think about how you would answer it. Moving on to 2.4 though, ecological tolerance. So our learning objective here is to describe ecological tolerance. You should be able to do text analysis on this. So analyze the author's claim based on what they're saying and the information that they're providing. So ecological range of tolerance is a range of conditions such as temperature, salinity, pH, sunlight, really a bunch of different things. Soil moisture is another one that maybe is more relevant to us. So our soil moisture on our eco column should be anywhere from about 10 to 45%. Anything below that, the plants aren't able to get enough water. Anything above that, it's too dense in water. So there's too much water there and not enough oxygen for the plants. but there's an ecological range of tolerance, whatever that condition is, that the organism can endure before injury or death results from it. So species and individual organisms both have a range of tolerance for all the different environmental conditions of their habitat. So if we're looking at species, certain species are obviously adapted to certain different conditions. You're not going to find a polar bear in the desert. So that species is more adapted to the conditions of the tundra than they are adapted to the desert. And individual organisms are also more adapted to a certain range of tolerance. So you or I might have different pool temperatures that we like. I mean, we can survive in them, but it's an example of how different individuals might have different tolerances. So an example is salmon have a basic range of tolerance between 6 and 22 degrees Celsius. Some individual salmon, though, have adaptations to give them a larger range of tolerance outside of that basic range for the species. And maybe there's some salmon that only like it 10 to 20 degrees, and so their range varies on an individual basis as well. So the ecological range of tolerance is species dependent as well as individual organism dependent. So this is temperature. So if we look at these different species and their ranges of temperature, we can see that some of these have cooler. So this weaver here has a cooler range of tolerance than maybe this gates here. They're obviously warmer. They like it right around 18 degrees. That's where they're most populous. But here, they are most populous around 15 degrees, but they have a larger range. You see a good amount of them around 10 degrees, and you still see a decent amount of them around 19 degrees. Whereas this gates here has about 15 degrees to maybe 20 degrees before they really start dying off. And I mean, even that is generous for their survival. This is a great example of a ecological tolerance graph where it's showing you down at the x-axis one of the conditions, like temperature, that it is susceptible to, and then it's showing you the species scope. And something important to point out is the ranges vary based on individuals because of genetic diversity, which is a good thing. We talked about that in 2.1. We also talked about that in Unit 0. Their ecological range of tolerance is species-based as well as individual-based because of genetic biodiversity. And it makes populations of salmon more resilient to disturbances. So if there's a couple sects of the salmon that are okay with warmer temperatures, those are the ones that are going to be more resilient to global warming. Those ones that are more susceptible to, or like cooler temperatures, though, are going to not survive global warming. So here's kind of a general example with pH and maybe temperature. So the preferred niche is where you're finding a majority of those surviving, the optimum range. So we're calling the optimal range is where organisms survive and grow and reproduce, where they're super happy, where they really like it, where most of them are surviving and almost all of them are reproducing. Then there's the zone of physiological stress, where organisms are surviving, but they're definitely experiencing some stress like infertility, their lack of growth, decreased activity, there's less of them, etc. And then we have the zone of complete intolerance. So zone of intolerance is the range where they will just die off. They're not able to survive that area. They either go through thermal shock or lack of food, lack of water, lack of oxygen, too high of pH, whether it's too acidic or too alkaline. There's 3 different ranges of ecological tolerance: optimal, zone of physiological stress, and zone of intolerance. And this is a great graph to show that right there. When you are writing FRQs for ecological tolerance, it's important to write for a specific kind of physiological stress. So our example is, are they experiencing suffocation? You have to denote a very specific example of physiological stress they're going through, because most of the time they're looking for you to identify that item. You can read through these on your own time. Great FRQ writing tips. I want you to it would be great if you guys would practice the FRQ. Here is the picture for the FRQ. It's a example because we're working on text analysis and we're working on identifying the author's claim. So using this to practice the FRQ and answering the question, great practice for FRQs for Unit 2. Otherwise, that is all I have. 2.5 is natural disasters and ecosystems.